To start off with, John Huff will talk about the soccer stadium. Although as a Dutchman, I should say that he really should be talking about the football stadium, but I'll leave it up to him. John, the floor is yours.
All right, thank you, Gerald, and thanks for having me on this series as well. I'm honored to be on here with Gerald, Joe, and Matt. It's pretty tall company. So, as Gerald mentioned, I'll be talking about the FC Cincinnati pile load test program. It's a job in Cincinnati, Ohio, where the owner selected to do some additional testing prior to finalizing his design that ended up saving considerable amount of time and money on this project. As I mentioned, my name is John Huff with Goettle. I'm one of our engineers. Let's see if I can get my slide to go forward now. There it goes. A little bit of a lag, but we'll make it work. So this presentation will I'll give you an introduction, talk about the stadium a little bit. We'll talk about some preliminary design considerations. Terracon did a geotechnical investigation report where they did some CPT tests across this site, and we'll look at a couple of representative ones of those and the preliminary pile design. And then we'll talk about a pile load test program that was performed, as I mentioned earlier, prior to the finalizing the design for the structure. We'll talk about the installation of that test program and the evaluation of the test program. Most of our time will be spent on items B and C here, and then we'll spend a little bit of time talking about project execution and then a quick summary. Major League Soccer is a pastime whose popularity is rapidly growing in the U.S. We're starting to see these stadiums pop up all over the place. You know, the DFI, this will be at least the second presentation we've done on one of those. We've already talked about the DC United up in DC, where Christoph Lokasol talked about head fixity and things like that, pile head fixity, I should say. But we're proud to have this one being constructed in Cincinnati. You know, the FC Cincinnati team here, people love the team. And they had a successful season a couple years ago in Nippert Stadium at UC as they started the construction of their permanent home, the stadium that we're going to talk about today in 2019. The proposed stadium was to be supported on augured cast-in-place piles. I'll call them auger cast piles today, just kind of for short or whatnot. And as the chairman of the auger cast and drill displacement pile committee, of course, auger cast piles are the perfect pile to use almost invariably. Of course, I'm joking about that, but you know, I'm a big believer in the fact that every project, every structure, and every subsurface has a best and most suitable foundation type. This one, it did turn out to be, you know, to be auger cast piles. Here's a rendering of the stadium before construction started. You can see it's really architecturally pleasing. It's got really cool vertical kind of rafters that give a wave effect on the side of the building. And we're really excited to add this structure to the Cincinnati kind of skyline. Here's one of the CPT borings that were done prior to construction. Basically, an SPT rig sampled the top 15 feet or so of each of these locations. They took blow counts and soil samples and whatnot from the top 15 feet, and then did a cone penetrometer test out the bottom. So you can see on these, there's not really any data in the top 15 feet. That's because that soil was augured and took blow counts and stuff like that. And then you can see, you know, variable soil layers. Matter of fact, let me see. I'm not sure if my cursor can be seen or not. I can't figure out how to turn on the laser pointer, but small soil or thin soil layers at the bottom, kind of layered with clays and sands. You know, there's some silty sands, some sandy silts, sometimes delineating between those and a cone penetrometer test can be tricky. So this is, like I said, this is one of the CPT logs terminated at just below 80 feet. This is boring along towards the north end of the site, FC7. You can see this one had a lot of the layering up in the 20 to 40 foot depth along the pile, and then it had a nice sand layer towards the, from 50 to 65 feet or so, 70 feet. But again, really mixed bag of soil layers throughout the profile of these piles. And again, the initial report, purely CPT data, at least below 15 feet, was used. The initial design was for a 300 kip capacity pile, groups of 300 kip piles to support columns, 3 and 4 pile groups for the heavier columns. The initial design was a 24-inch diameter auger cast that's 80 feet long. And the construction manager on the job asked Goettle to do an initial budget on these 24-inch piles. There were several hundred on the job. The initial budget was $10.5 million. And part of what we were looking at least initially, the 24-inch, 80-foot long piles really looked like a robust pile for just a 300 kip pile design load. So just taking a quick kind of back of the napkin calculation, if you think you're going to get an allowable end bearing, let's just say of 40 KSF times the 3.14 square feet of end bearing at the base of the pile, you can shed 125 or resist 125 kips in end bearing of pile capacity. So you can take that off the required design load. You need to have enough contact area on the sidewalls of that pile to get, let's say, 175 kips. Now you may get a little bit more, maybe get a little bit less in allowable end bearing. So that 175 may go a little bit up or down. But if you look at this 80-foot pile and compute the sidewall contact area of the underground column of grout with the soil, surrounding soil, you would only need a unit skin friction of 0.35 KSF, allowable skin friction, which is very, very low. I mean, you may get something that low up towards the top portion of the pile when you're in those weak clays. But towards the bottom where you're starting to see some of those sand layers, we've tested piles in the Ohio River Valley and in this area of Cincinnati where you get 2 to 3 times that, even an allowable unit skin friction. So part of what we did in the initial budget was budget a smaller pile that may be a little bit more aggressive, considerably more aggressive pile design for our client. And what that consisted of was 18-inch diameter piles, so smaller diameter, and also shorter depths. This was a considerable change, and the owner and the GC contracted with Goettle to perform a pre-production pile load test program before they finalized their pile design. So they elected to make a $275,000 investment before they mobilized their construction crews and all that other stuff to the job site to perform a standalone load test program. And what that $275,000 got them was 2 additional SPT tests. Because an SPT test, you can sample the soil, bring it up out of the hole, and you can delineate between those sandy silts versus silty sands and this other stuff that sometimes is, you might make a conservative estimation from CPT data. You can see with confidence, okay, this soil layer is primarily sandy. We can get better skin friction out of it, and things like that. So it included, in fact, I think we show this on the next slide, 2 SPT soil borings at each test location. We set up a test location on the north side of the site and a test location at the south side of the site. And at each of those 2 sites, we did a SPT boring at each of them. And we did a long pile and a short pile, basically. So the north, we had a 65-foot pile and a 45-foot pile. And at the south, we had a 65-foot pile and a 45-foot pile. And we ran all 4 of these static compression tests. And we put the SPT borings on purpose very close to the test locations so we can we can correlate solar layers with frictional capacities and so on and so forth. So this shows a plan view of the site. You can see it used to be an existing football practice field that was taken down, and there were some other surrounding structures that were demoed for the construction of the soccer stadium as well. But you can see test piles 1 and 2 towards the southern edge of the site, and then test piles 3 and 4 up towards the north. This shows those same two test piles, just kind of overlaid with the soccer stadium foundations coming down, or football stadiums foundations coming down for Gerald there. And again, short pile and long pile to the north for test piles 3 and 4, and then a short pile and long pile for the south for TP 1 and 2. And a 45-foot pile is a quite aggressive design to support a 300 kip load, because you want to prove 600 kips ultimate capacity in your load test program. But doing this program prior to finalizing the design and prior to getting everything out there is you can afford to take at least an optional aggressive design, because you've got some cushion on the tail end to evaluate things and tweak your design to right at a safety factor of 2, or as close as you want to get to a safety factor of 2 prior to finalizing the cap design, pile layout, and things like that. This shows our 4 reaction piles and a static compression test pile, and then just kind of graphically where SBFC3, which is a supplemental boring, 3, which is that additional SPT test boring that we performed right by the load test program. So here's the log of SFC3. You can see similar layered effects: silty clay, silty sand, silty clay, silty sand, and so on. But you can see really some good blow counts in a lot of those sand layers, 28, 30 blows. So you could expect to get really, really nice frictional capacity in those layers that are only 35 to 45 feet down. This is a continuation of that boring from 45 down to 90 feet. You can see one more little sand layer there, and then the rest is clays and silts layered within each other. Typical pile load test program setup. We had 2 of these, as I mentioned. Basically 6 reaction piles. The 2 reaction piles in the center are basically used for each test pile. They're used twice. We'll set up the frame over the left group of 5 piles first, and then flip the frame over to the right-hand group of 5 piles, and test these 2 compression test piles in pretty close proximity. This shows the test beam that goes over top of the test pile, and then the 2 reaction beams. They're double beams that are kind of strapped together. You can fish the reaction bar up through the reaction beams, and anchor this test frame down on top of the pile and apply the load vertically down on the 18-inch diameter test pile. Here's a picture of the pile installation process. This isn't actually the test pile installation. You can see we have 2 rigs running here. So this was for production pile installation, but you can see a crane and leads rig with CFA auger running up those vertical leads. The leads are marked vertically. I'm sure pretty much everyone on this call has seen pile installation like this. Basically, you drill down with a hollow stemmed auger, pump fluid grout through that hollow stem. As you're extracting the auger, you'll pull that drilling lead off once you've finished pumping out of the pile, clean the top of it, screen the top of it, set the reinforcement in that fluid grout column, and you're left with an underground pile that's suitable to transfer load down to better soil layers than are at the surface. Here's a picture of the test setup. You can see the test beam running across that beautiful rust-colored beam, and then 2 white sister beams or reaction beams at the top. You can see a metal angle iron load or independent reference rail on either side of that orange jack that the dial indicators are attached to with magnetic bases, and then the dial indicators evaluate the head deflection, downward head deflection at a given load. Just a little side note. You can see where we have tents over top of this angle iron. It's important to keep direct sunlight, as much direct sunlight as you can at least, off of that independent reference rail and off the dial indicators. When the direct sunlight hits them, you can have thermal expansion in those reference rails, and they can move slightly. And if the reference rail moves, your dial indicators move and can give you a little bit of an effect on your dial indicator readings. So it's important. You can see in this job, we initially set the white tent up to block the noonday sun. I think the sun got low enough in the day to where these the shadows are running kind of sideways on this one. You can see we set the navy tent up to the left here to try to keep as much of that sun off of that reference rail as you can. We'll look at each of the 4 load test plots. This is the first pile, test pile 1, 18-inch, 65-foot long. This one actually went 63 feet for whatever reason, but we'll just call it a 65-foot pile. You can see very linear response in the first 300 kips, and then stays very well linear to the next, all the way up to 600 kips. Deflection at 300 kip design load is under 0.2 of an inch. So this pile, I mean, we ultimately got it up almost to 900 kips before it started to plunge. So this pile, you could argue, if the design load on it is 300 kips, it has a safety factor almost of 3. As a point of reference, we included the theoretical elastic line in red. That basically models the deflection of the pile if it were just in space without soil around it, just using elastic theory. And then the blue line is the Davison offset line, which may or may not be appropriate to evaluate the ultimate capacity of an auger cast pile, but that was just attached there for reference. If you were using the Davison offset as the most conservative evaluation of the ultimate capacity of this pile, you can see it crosses the Davison at 700, call it 750 kips. But there are other ways to evaluate the ultimate capacity of the pile that would give you closer to an 875 kip ultimate capacity for this first long pile. TP2, which tested right beside TP1, you can see here was 18-inch diameter, 45 feet long. Very similar deflections at 300 kips. This one ended up plunging right at 600 kips. We got the load slightly above 600, but it already kind of started that plunging failure. You can see it turned vertically really nicely right at 600 kips. So depending on how you evaluate this pile's ultimate capacity, this pile has close to a factor of safety of 2. Test pile 3, similar curve shape as test pile 1, the other 65-foot long pile. You see it exhibits clear plunging behavior at 800 kips. So still a safety factor well over 2, close to 3, again, similar to the other longer pile. And then TP4 exhibit plunging behavior, started to as we passed 500 kips, and then ultimately plunged at 560 or so kips. So just under a safety factor of 2 on TP4. Another interesting thing that we found on these is if you look at TP1 and 3, you can see for the first section of load deflection curve until you get to 500 kips or so, the actual load deflection plot is above the theoretical elastic deflection. So you know as you're evaluating that one, and we'll slide back over to TP3, it's similar. There's a gap between the load deflection line and the theoretical elastic line. There's that gap, which tells you a lot of the load's being taken up above the toe of that pile. Not much, if any, at those loads at least, of the applied loads getting down to the bottom of the pile. On our 2 short piles, you can see it tracks very closely to the theoretical line initially, which tells you a little bit more of that load's getting down closer to the bottom of the pile, which is what you ultimately want. But it was interesting to us that it tracked very closely with the theoretical elastic line for the 2 short piles, and then stayed above it considerably for the 2 longer piles. So ultimately, 18-inch diameter, 65-foot long auger cast piles were selected. An argument could be made that you could do something shorter than 65 feet because each of the 65 footers on the load test program were close to a safety factor of 3. They were well above 2, 2.5. But nonetheless, the design was kind of finalized for 18-inch diameter, 65 feet long. They finalized the reinforcing design, cap design, pile layouts within the cap, so on and so forth. You know, with a smaller diameter pile, the caps get smaller because the pile spacing is a function of the diameter. And once all that was finalized, the project, a little bit to Goettle's dismay, was sent out to competitive bid. We were kind of hoping that we would be able to negotiate the project after that load test program, but it was sent out to our peers, you know, the premier pile contractors in the area. And thankfully, after the competitive bid process was executed, Goettle was the low bidder at $6.1 million. So you can see over $4 million in savings from the initial design to the finalized design that was done after that $275,000 investment of a pre-production pile load test program. Keep in mind, only about half of that, they were going to run a pile load test program regardless on the job. So only about half of that was actually a premium to the project. The cost of mobilizing a drilling rig out there and then demobilizing it in a separate mob is really the only actual cost of the project. So it's actually probably closer to half of that $275,000. But anyway, the owner benefited in cost savings for the piles. Caps got smaller. We don't know exactly what the savings were in the caps, but they were probably considerable, and there were schedule savings as well. Really quickly, some of the project execution pictures. You can see an aerial picture here. 2 piling rigs, one along the north side, one at the south side. You can see some assist cranes like that. This project was all done with 2 piling rigs. Another aerial photograph from roughly the same angle shows, I'm going to say it was a year later, shows some of the structural steel being set. You can see some of those canopies starting to take shape around the top of the stadium. All the seats in the stadium will be under shade, which is kind of a neat, it'll be open air through the center, but all the seats will ultimately be under shade. The canopies come out far enough to do that. I thought that was a really neat proposition for this stadium. But you can see here just an aerial photo of the project execution. In summary, although CPT data provides, CPT tests provide valuable geotechnical data, we always perform at least some SPT as well. I hear it all the time that SPT data, the SPT test was developed in the early 1900s. You're living in the past if you're still looking at SPT. In reality, a lot of the equations we use to design piles were also developed in the early 1900s. So, and the added benefit of just being able to see the soil cuttings and things like that enables us as pile designers to design with a little bit more certainty, and that's just in our estimation. Secondly, pre-production, pre-bid load test programs can often provide valuable data for cost and schedule savings. So some of the added testing that this client did on the front end, I mean, the SPT was good. The standard penetration tests, the 2 extra ones they had us do, were nice. They were good, but really the main benefit were those sacrificial load test programs that were done prior to finalizing the design. And thirdly, trust the input of reputable geotechnical contractors and engineers with experience in that area. They can provide a lot of benefit early on in projects like these. And the owner benefited a lot on this project doing that. So that's all that I have.